So today we are going to learn an important topic called Paracore. Paracore. Okay, and let us consider a liquid with a density D. The density of a liquid that we are considering is D, capital D, and this liquid has a surface tension, okay, and that surface tension is equal to gamma, and this liquid has a vapor, and the density of that vapor is density of vapor is equal to small d. Okay, so this is the liquid that we are considering, a liquid of density d, of surface tension gamma, and the vapor density d, small d, at a temperature, a particular temperature T. Okay, and then there is a relation between this d, gamma, and d, and this relation is gamma raised to 1 divided by 4 divided by d minus d is equal to c, where c is a constant. So if we are multiplying this equation, let me call this as equation number 1. If we are multiplying this equation number 1 with a molar mass mm, okay, if we are multiplying this both sides, left hand side and right hand side, we will get molar mass mm gamma raised to 1 divided by 4 divided by d minus d is equal to molar mass mm into C, and m into C can be called as another parameter, and this parameter is called a paracord. Okay, this is called a paracord. Okay, sorry. This is called a paracord. And paracore is therefore the product of molar mass M and C, where C is gamma raised to 1 by 4 divided by D minus D. And why we are introducing this term paracore? We are introducing this term paracore because paracore is more useful than the molar volume, more useful than molar volume, that is Vm, in deciding between two alternative structures of a compound. Okay, you can consider a compound, and this compound can have two alternative structures, and you wanted to know which alternative structure is correct, and you have to depend on some parameter, and instead of depending upon the molar volume, a better parameter is paracore P. Okay, that is why Paracord is very important, and it will give some structural information. So this is a non-spectroscopic method to get the structural information of the compounds. And now we can suppose that d is very small, which the small d is very small because that is the density of the vapor. The vapor already is not very dense, and therefore the density of the vapor can be neglected, or d is very small compared to the capital D. Okay, therefore in that case we can write that d minus d is equal to or almost equal to capital D, because small d is very small. And in that situation, we can write the above equation, that is equation number 2, the equation for the paracore. This is equation number 2. We can write this equation number 2 like m gamma raised to 1 divided by 4 divided by capital D. Instead of D minus D, we write D, that is equal to mmc and mm C, and which is equal to Paracore. Okay, and suppose that we are considering a particular temperature. We are considering a particular temperature at which the surface tension is unity. Okay, we are considering a particular temperature at which the surface tension of the liquid is unity, and in that case means if gamma is equal to 1, in that case this equation becomes by d or into gamma raised to 1 by 4 is equal to uh, into C, that is equal to P, right? So gamma raised to 1 by 4 will be unity. So we can write it like divided by D is equal to P. Okay, we can write it like this. And divided by D means molar mass divided by density. That is the molar volume. Mass by density, that is volume. Okay, so this will give the molar volume Vm, and in that particular situation Vm become equal to Paracore. So when Vm or molar volume will become equal to Paracore, and that is happening when the surface tension of the liquid is unity. So we are considering a particular temperature at which the surface tension of the liquid is unity, and in that circumstance the molar volume will be equal to Paracore. So this is important because this directly give a definition to the Paracord. So from this one we can define Paracord as the molar volume of a liquid. Paracord is the molar volume of a liquid at a temperature at which the surface tension is unity. So what is Paracord? Paracord can be defined as the molar volume of a liquid at a temperature at which the surface tension is unity. Surface tension unity ആകുന്ന കേസിലുള്ള മോളാർ വോളിയമാണ് ആ ഒരു ലിക്വിഡിന്റെ പാരക്കോർ എന്ന് പറയുന്നത്. Okay. Now we are going to consider this paracore in a little bit more detail. Actually, we have to consider that the paracore as an additive property. Paracore is an additive property. But additive property means we can add up the contributions from different parts, and the sum of those contributions will be the total paracore of a liquid. Okay, I will explain it. So by saying that this is an additive property, definitely there will be some contributions, individual contributions, and these individual contributions will be added up to get the total paracore. And these contributions are coming from the atoms. So atoms, the first contribution is from atoms present in the molecule, which constitutes the liquid, and the second contribution is coming from the constitution of the substance, constitution of the substance, or simply the structure of the substance or the chemical structure of the substance. So the contribution towards the total paracore will be coming from the atoms and also the chemical structure of the molecule. And if the contributions are coming from the atoms, or the contribution towards the total paracore from the atoms, are called atomic paracore, atomic paracore, atomic paracore. And the contribution from the structural features of the molecule is called as structural paracores, paracore, structural paracore. Okay, so structural paracore and atomic paracore are there, and atomic paracore means the contribution of the atoms or various atoms towards the total paracore of the liquid is called atomic paracore, and the contribution of the various structural features towards the total paracore of the liquid is called a structural paracore. And now we are going to look into the atomic paracore and structural paracore in more detail. Okay, I said that the atomic paracore is the contribution of the atoms towards the total paracore. So different atoms will have different contributions. Okay, if you are speaking about the atomic paracore, different atoms will have different contributions towards the total paracore of the liquid. For example, carbon will give a contribution of 4.8 towards the total paracore, and hydrogen atoms will give a contribution of 17.1 towards the total paracore. And oxygen atom will give a contribution of 20.0 towards the total paracord. Okay, so these type of contributions are called atomic paracord. So from this one we can determine the we can determine the paracord of decane. For example, decane. Okay, decane is C10H22. Okay, this is decane, and we can determine the paracord of this compound. How we can determine the paracord of this compound? We have to look into the atomic contributors. The atomic contributors here are carbon and hydrogen. So we can calculate the total paracord of this molecule. There are 10 carbon atoms, so 10 into 4.8 plus there are 22 hydrogen atoms, so 22 into 17.1. Okay, so if you are calculating this, we will get a value 424.2. So this is the total paracord of decane. So total paracord of the decane can be calculated from the atomic paracords of carbon atoms and hydrogen atoms. Okay, so that's about atomic paracord. And now we can look into the structural paracord. Structural paracord. Structural paracord. Okay. And now let us calculate. For example, we already know that there will be contribution of the atoms towards at the paracore. So we can calculate, for example, the paracore of ethylene, paracore of ethylene molecule. Okay, ethylene is C2H4. We can calculate the paracore of this one from the atomic contributions. So there are two carbon atoms, therefore 2 into 4.8 plus there are 4 hydrogen atoms, so 4 into 17.1, and if you are calculating this is equal to 78. So we should expect that the paracord of ethylene is 78. But if you are measuring the paracore experimentally, the actual value of the paracore is equal to 99.5. So 78 is not the correct value that we have calculated already from the atomic contributors, but we have to get a value which is 99.5. It means that some contribution is missing in C2H4. What is the structure of C2H4? H, Z, H, double bond C, H, H. So two carbon atoms are connected by a double bond. So where will be the additional paracord coming from? The additional paracord or the difference is 99.5 minus 78, that is equal to 21.5, and if this difference must be coming from this structural feature. What is that structural feature? That is the carbon-carbon double bond. So there should be a contribution from the carbon-carbon double bond, and this contribution is adding with the atomic paracores, and then we get the total paracore which is 99.5. Therefore, the carbon-carbon double bond in this molecule must have contributed 21.5 towards the total paracore. What does it mean? Not only the atoms which contribute towards the total paracore, but the structural features of the molecule will also contribute towards the total paracore. So that is called a structural paracore. Here there is a structural feature. The structural feature here is the carbon-carbon double bond. The two carbon atoms are connected by a double bond, and that particular structural feature is contributing towards the total paracore of the molecule, and that is called the structural paracore. So structural paracore is the contribution of the structural features of the molecule towards the total paracore. And even if we have calculated the contribution from the carbon-carbon double bond, in this case is 21.5, in the case of ethylene, we can see that the average contribution of the carbon-carbon double bond or any double bond, okay, is 23.2. If you are considering many examples, so not only we are considering the example of ethylene, we can consider n number of examples with the double bonds, and if you are looking into the Paracore values contributed by these double bonds, we can see that the double bond contribution the average contribution of the double bond in the organic molecules will be 23.2. Okay, so we have to consider this as the actual value for the average contribution of the double bond. Okay, now you know about the atomic paracord and the structural paracord. Now we have a table which lists all the atomic and structural paracord, and I am going to put that table here. This is the table which lists all the atomic and structural paracords. Okay, I have given many atomic and structural paracords in this table. You can see carbon, hydrogen, nitrogen, oxygen, chlorine, bromine, iodine, sulfur, phosphorus, and the corresponding atomic paracords here. And also I have given the structural paracords for double bond, triple bond, dative bond. You can look into the double bond 23.2. Okay, and three-membered ring will contribute 16.7. Four-membered ring 11.6, and six-membered ring 6.1. For example, if there is a benzene ring, that ring will contribute 6.1 to the total paracord. Naphthalene ring 12.2, like that. Okay, so I have given many structural paracords also in this table, and we can use this table to calculate the paracord of the organic molecules. For example, we will use this table to calculate the paracord of a simple organic molecule, that is acetone. Okay, we can calculate the paracord of acetone. What's the structure of acetone? CH3, Z, again CH3, and C is connected to oxygen through a double bond. So CH3, COCH3, right? That's acetone. And now we can calculate the paracord of this acetone molecule. What are the atomic contributors? 3 carbon atoms are there. So 3 carbon atoms will contribute 3 into, look into the table, what is the contribution from the carbon? The contribution from the carbon is 4.8. So 3 into 4.8, 4.8, and there are 6 hydrogen atoms, right? 6 hydrogen atoms. So 6 hydrogen atoms will give 6 into, what is the contribution from the hydrogen? Contribution from the hydrogen is 17.1. So we will write 6 into 17.1. And there is 1 oxygen, right? So 1 oxygen, 1 O, and that will contribute 1 into, what is the contribution of the oxygen? We can look into the table, and the contribution of the oxygen is 20.0. Okay, we can write 1 into 20.0, 1 into 20.0. So these are the atomic contributors. Now we have a structural contribution also, because there is a carbon oxygen double bonds. So there is one double bond, and this one double bond will contribute 1 into, what is the contribution from the double bond? We can look into the table. The double bond will contribute 23.2. So let us write 1 into 23.2, and now we can calculate all these. 3 into 4.8, that is 14.4, and 6 into 17.1, that is equal to 102.6, and 1 into 20, that is equal to 20, and 1 into 23.2, that is equal to 23.2. And if you are taking the sum of all these, then we will get the calculated value of the paracord. Okay, the calculated value of the paracord, and that is equal to 14.4 plus 102.6 plus 20.0 plus 23.2, and that is equal to 160.2. Okay, that is the calculated value of the paracord. And do you know what is the observed value? Means experimental value. Observed value of Paracore in this case is equal to 161.1. See, look at the agreement. The calculated value is 160.2 and the experimental value is 161.1. They are very close to each other, and therefore there is a very good agreement between the calculated value and the observed value. Okay, so what do you understand from this one? And we can understand from this one as that we can experimentally calculate the paracord, and from this paracord we can know what is the structural features, because these structural features only will contribute towards the Paracore to get 160.2. Okay, so Paracore is a good indication towards the structural features of a molecule. So that is an important application. In order to understand this important application of the Paracord in deciding the structure, let us take another example. So application of the Paracord in deciding the structure. Let us consider a structure That structure is quinone. Okay, you already know this structure, quinone. Okay, this quinone molecule is its molecular formula is C6H4O2, and for this one we can consider two structural variants. One structural variant is like this. Okay, this is one structural variant, double bond O and double bond O. Okay, there is one structural variant. Let me call this as a structure 1, and let me consider another structural variant. That is, I will consider a ring like this. Okay, a ring like this, and this is like a benzene ring, and there will be bridging oxygens like this O. Okay, this is another structural variant. Both of them will have the same molecular formula. This is also C6H4O2. This is also C6H4O2. Okay, so this is structure 2. So there are two structural possibilities for this quinone, and we are going to determine which structure is correct from the Paracore value. Before considering the Paracore values from the atomic and structural contributions, I will give you the observed value of the Paracore. Observed value of Paracore. Observed Paracore. In this case, in the case of quinone, is 236.8. 236.8. This is the observed value. Okay, 236.8. So we will calculate the Paracore value of the structure 1 and structure 2, and we will see which one is closer to 236.8. Whichever is closer to 236.8, which is the observed value or experimental value, that structure will be the acceptable structure. So let us calculate the structure, the Paracore value of structure 1. Structure 1 has 6 carbon atoms, so 6C, that is equal to 6 into 4.8, that is equal to 28.8, and it has 4 hydrogens. 4H is equal to 4 into 17.1, no, minus 4, 4 into 17.1, that is equal to 68.4, and there are 2 oxygen atoms, 2 oxygen, that is equal to 2 into 20.0, that is equal to 40.0, and there are 4 double bonds, right? 4 double bonds, one double bond here, one double bond here, one here, and one here. So there are 4 double bonds, and 4 double bonds will contribute 4 into 23.2, that is equal to 92.8, and there is a 6-membered ring, right? There is a 6-membered ring, so we have to calculate this also. 6-membered ring is there, and this 6-membered ring will contribute 6.1. You can look at the table. There is 6-membered ring. 6-membered ring is 6.1. Okay, so these are the atomic and structural contribution towards the Paracore. And if you are taking the total of all these one, we can get the value 236.1. Okay, 236.1. Now let us calculate the Paracore value of the structure 2, and there are also 6 carbon atoms. From here to here, all are same. 6 carbon atoms, 4 hydrogen atoms, and 2 oxygen atoms. Okay, So we will take this calculation here also. So this is same here also. 6 carbon atoms, 4 hydrogen atoms, and 2 oxygen atoms. And then we have how many double bonds here in this one? 1, 2, 3. 3 double bonds only. So we have to write 3 double bonds here. Okay, 3. Sorry, 3 double bonds, and 3 double bonds will have a contribution of 3 into 3 into 23.2, 23.2, that is equal to 69.6, 69.6. And in this structure we have how many 6-membered rings are here? How many 6-membered rings? And we can look at the 6-membered rings here. Okay, so this is one 6-membered ring. Let me take another brush in order to show which are the 6-membered ring. So this is one 6-membered ring. Okay, this is one 6-membered ring, and this is another 6-membered ring, right? And there is another 6-membered ring here. This is also another 6-membered ring. So totally there are six, no, no, it's 3 6-membered rings. 3 6-membered rings. Okay, 3 6-membered rings. So 3 6-membered rings will give its contribution. So let us write 3 3 6-membered rings. 3 is 6-membered rings, and 3 6-membered rings will give a contribution of 3 into 6.1, 6.1, that is equal to 18.3, 18.3. So what are the difference here from the structure 1 and structure 2? Here 4 double bonds in structure 1, but in structure 2 there are only 3 double bonds. And in structure 1 there is only one 6-membered ring, but in structure 2 there are 3 6-membered rings. So if you are taking the total of all these one, we will get a value 225, 225.1, 225.1. So which is the closer value to the observed paracord? Observed paracord is 236.8, 236.8, and the calculated values are 236.1 and 225.1. Obviously the first one will have an agreement with the observed value, so this is correct one, right? So from this one we can guess that the structure of quinone is not structure 2 but structure 1. This is the structure of quinone. This diketone structure is the correct structure of quinone, and this important information we got from the Paracore value. So Paracore is an important parameter to decide the structural features of the organic molecules. Okay, so I hope you understood the idea of Paracord and what is its importance and how paracores are being contributed from the atomic and structural features of the molecule and all these things. If you have any doubt, don't hesitate to ask me, and thank you for watching and stay tuned.